you've got a whole bunch of properties again. And all of these properties we've worked with. And I've got a handout with all this on here so you don't have to worry about writing it all out. And if you recall when we worked with properties and exponents last time around when we're dealing with integer values, you had to add or subtract exponents depending upon if you were multiplying or dividing. You had to have power of powers if you were multiplying out, raising the different exponents. You had a lot of different things to go through. Well, none of these properties change at all if you're dealing with rational exponents. They all hold true. The only thing that's going to be a little bit scary is that you're going to have to deal with a fraction. But if you have to add or subtract multiplying fractions, you do all have the capacity to use a calculator. So don't freak out when you see these things. Let's walk through a couple of them together. Again, as we set up these guys here, I have the same base with different exponents, and I'm multiplying them. When I do that, I have to add my exponents. What's 1/2 plus 3 halves?
4 for 2, 2.
4 halves, which gives you
2.
Good. And last time I checked, 3 squared is? That doesn't change. You're using the properties of exponents. You're adding, since they have the same base. Same thing with 2. You've got a whole bunch of junk raised to an exponent, so you have power to power. When that happened, you had to multiply your exponents. What's 3 halves times 2?
3.
Yeah, 6 halves, so you get 4 to the 6 halves, which is 4 cubed. And last time I checked, 4 cubed is?
36.
4 to 64.
I don't know why that's a dig on him. That's
funny.
impressive. All right. Again, you've got 2 things within parentheses being multiplied together, and they're both being raised to the 1/2 power. When you've got junk inside parentheses over multiplication, you're basically distributing the exponent then. What did 1/2 power mean? Remember? Square root. So this is telling you to take the square root of 9 times the square root of 4. What do you get?
6.
Good. Remember, you're taking the 1/2 root of 9 and you're taking the 1/2 root of 4. 1/2 root means square root.
So 3 plus 2. No, 3 times 2.
Correct.
6.
3 plus 2 would have been 5. It would have been wrong. But, you know, it's essential. Now, Kayla's favorite thing in the whole wide world were negative exponents.
Oh, it's just, it's 1 over 5. Right?
So again, this becomes 1 over 25 to the 1/2 power, which is 1 over 5.
Why?
Kayla.
Remember,
No, I don't get why you put the 25 under 1.
because
25 is not negative.
the 25 is not negative, but it's being raised to a negative exponent.
But it's
Yeah, but isn't.
But it's still a negative exponent.
It's not.
It's not happy. The 25 isn't happy because the exponent's negative. It wants the exponent to be happy. It wants to take its best friend somewhere to make him happy. It wants to take it to its Chuck E. Cheese. It
I
took it
wouldn't
to
really call them
it would. It's really not. I've been there with my children.
No, it's better.
Same idea when you get to the next value. Again, when you're dealing with same bases and you're dividing, remember how we set these things up? We played that game of war. In this case, when we play that game of war, who wins? 5 halves or 1/2?
5 halves. 5 halves.
So what's 5 halves minus 1/2?
3, 4, 2. 4 halves.
4 halves. So you get
1 squared is 1. Is that right? No, 6.
it's not. You're working with the exponents. The base doesn't change.
I thought.
Nope.
What? I thought
The base doesn't change.
Wait,
I
Think back when you had.
your full numbers first and then like divide them out.
No. Think about what you did before. You had x to the 5th over x squared. Did the x's just disappear? And you get 3?
No, you don't.
No.
You don't.
Then you'd be wrong. You just add x to the 3rd. It's the same idea. It's the same premise. It's the same process. It's the same process. The
What
same
happens
rules.
to the others?
It's the square root of 6. It's the square root of 6 to the 5th power divided by the square root of 6. Your exponents work out because you have the same base. If you subtract the exponents, you get 4 halves.
So when you subtract the exponents, the 6 goes over.
So all you have to do is.
So otherwise, there'd still be over 6, and then be back to 6.
Right.
Not the case at all.
And then the last one mirrors the one we did where it was 9 times 4 all to the half power. In this case, it's 8 over 27 all to the 3rd power, which means what's the 3rd power mean again? Cube root. So again, this means that you have the cube root of 8 divided by the cube root of 27.
2 and 3.
Very good. Your exponent rules do not change here, guys. They all mean the same thing. You just have to deal with them with a fraction now. So you just have to watch how you set them up. All the rules still hold true that we've done before. As we get into this a little bit more, you'll start to see that things start to get a little bit messier when we start throwing some variables in here.
Ooh.
But we'll get there. Let's just try a couple of these to start with. 5 to the 1/2 times 5 to the 1/4.
5 to the 3rd.
Do I have the same base?
Add them 3/4.
So I have to add the exponents. What's 1/2 and 1/4?
3/4.
3/4. My answer would be, you don't have to worry about it. Here's the general rule with all of these style problems. If it starts with an exponent, starts with a rational exponent, you leave it as a rational exponent. If it starts as an nth root, excuse me, you know, it's got the square root in there, you leave it with the square root in there. I'll show you examples of both styles today. Okay? Here again, I have 7 over 7 to the 1/3. Is it the same base? Go ahead. Go ahead. I appreciate you worrying. Is it the same base?
No.
Not at all.
Last time I checked, 7 is the same number, isn't it?
Okay.
What's the exponent in the numerator?
1.
1. Who wins, 1 or 1/3?
1.
What's 1 minus 1/3?
2/3.
And you leave it. Who wins in the battle of war again? Is 1 bigger than 1/3? Yes. That's why it stays up top.
Wouldn't it be 1? Or you would have to put 7 over 7 to 2/3 power over 7, then, right?
Nope.
I've never seen a 1/3 power.
When you divide
Nope.
the 7.
Again, if this was the same idea as x to the 4th over x to the 3rd, who wins in the battle of war?
X to the 4th.
The 4th. What's 4 minus 3?
1.
X.
It just stays there. It's following the same rules. There's nothing, it goes away. Your exponent,
But if you had a number, like for x, you would divide the 2x.
no. Oh, if you had a number in front of it, you had a coefficient, yeah, then you would worry about that. I'm not dividing 7. 7 is the base. It has the same base with different exponents, so all I do is deal with the exponents. Okay? Since 7 here are the same, these are just the same bases. Since those are the same bases, you work with the exponents, and that's how it sets out. There's nothing else to worry about. Yeah?
So like you couldn't do like 3 to the 1/8 power over 5 to the...
No, because they don't have the same base. There's nothing you can do with that. There's nothing you can simplify out. Yes, ma'am.
What if the exponent in the denominator?
Was bigger?
Yeah.
Then it would stay in the denominator like it did before. So if it was the same idea, if this was x over 4 over x over 30, it became 1 over x to the 26th. It won the battle of war in the denominator.
It stays.
Yep. You stay and keep it as a positive exponent, whether it's on the numerator or the denominator. It's all the same rules as it was before. All right? Same exact rules. This one gets a little messier. Yeah.
Mom just said, how do you know that, well, I mean, how do you know how far to go? Like, how do you know if you should have a 7 to the 2/3, or if you should have like 1n root a parentheses m? How do you know like how far you should go into solving?
If you're simplifying radicals, you're simplifying rational exponents. You want a positive exponent. Simplify it as far as you can. If it's like 6/2, you write it as to the third. If it's negative 6/2, you got to make it 1 over something to the third. That's what you're looking to do. You're not changing it from one to the other in these style problems. You're just simplifying it as far as you can go down here. That's all we're doing. It just takes time to get accustomed. You've never seen this. It takes a couple of examples. Okay. Now in this case, hold on a second. Okay. In this case here, you've got same base, same exponents within the parentheses, all raised to another power. Now, when you have same base, or excuse me, different bases with the same exponents, think about some of the properties that we have. This is the same thing as saying 12 over 4 to the 1/3 squared.
So you can do 3.
Exactly. If you look on that property sheet, the last property on there, what I did is I did the reverse. I went from right to left. Since both parts of the numerator and denominator are the same exponent, I took it out. From there, I can simplify the fraction and get 3. And now I have power to power, which means I just have to multiply my exponents. What's 2 times 1/3?
3 and 2/3.
What is it?
3 and 2/3.
Oh, I'm sorry. I thought you said 3 2/3 or something.
Oh.
I just want to make sure. Yes, it's 3 2/3. Again, all I'm doing is using the same properties that we've had before in chapter 6, working back and forth with fractions now. That's all. The rules here have not changed. It's just a fraction you have to work with. And again, these same style rules don't change when you work with n root. I always say that wrong. Okay. I think that working with the root ones tend to be a little bit easier than exponent ones.
Wait, don't you have to distribute the second power as through
No, because it's something to do with it's power to power. When you have power to power, you just multiply your exponents and you're done. That's all it is. And this is a reminder of what the root stuff looks like. This is stuff that we've all worked with some of the properties of radicals. If you think about how you guys simplified radicals throughout. Remember, if you just have the square root of 12, what was the n value of a square root of 12? What's the n value there? It's the square root. It's 2. We never said that. We never said it was the nth root. We never said it was a second root of 12. We just call it a square root. What we did with those things, we went to simplify them. You went looking for perfect squares.
So you got to find 3 plus 3.
Yeah, you're going to find perfect cubes or perfect fourths, perfect fifths, things like that. When you simplify out, you were able to break it apart as the square root of 4 and the square root of 3. This is using those product properties. This is stuff that we have seen, and you would wind up with 2 root 3. Those rules don't change when it has an n value in there. Just the complexity of the problem does, where you might have to find a perfect cube. And we have plenty of examples of that stuff today. Same thing with the quotient stuff. When we had fractional roots, we had to split it apart, simplify, and then we had to rationalize. Remember, we did not like to have square roots in denominators. We don't like to have nth roots in denominators as well. So we have to work on setting those up. Out of all the stuff we do today, rationalizing of an nth root is the most complicated. As we get into this stuff, the other simplifying of the nth roots you're going to find to be pretty straightforward. All right? So let me show you a couple of these. Cube root of 4 times the cube root of 16. Do I have the same nth root? Okay. Since I have the same nth root, that means I'm allowed to multiply the stuff underneath the radical. What's 4 times 16?
64.
64. What's this cube root of 64? 4. And there's your answer. Again, I had the same nth root. I can multiply the junk underneath it. Okay? With the division one. But again, do they have the same nth root?
So just divide.
So
81.
again here, I have the same nth root, right? I have the fourth root of 164 or 162 over the fourth root of 2. Since those guys have the exact same nth root, what can I do with the stuff under the radical? Divide it. What's half of 162?
81.
81. Right. And what's the fourth root of 81?
3.
Yes. Here's the one thing I will say when we're just doing the simplifying. In this section, with the numbers, they don't really go plus or minus a lot. I don't know why they waver away from it. But when you get to the variables, they will always say that assume that all variables are positive. They will say that, okay? When we get to quizzing and testing and things like that, the one, I think, generic rule that I will state as far as plus minus is when you take an even root over an equal sign, you have to take it on both sides, that's when you have to, I'll make sure you guys are required to have your plus minus. When you're simplifying like this, you can just leave it how it is. Does that make sense?
So like you gotta divide it.
What's that? No, what you were saying about being plus minus.
No, like, so if it was an example like x minus 2 to the fourth.
The quantity or something?
Yeah.
Yeah, when you take it equals 81, then you have to take the fourth root of over both sides. That's when you have to do plus minus. When you're simplifying, it's not that big of a deal. We'll be okay with that. Does that make sense, Cal? All right. All right. Again, going simplified form. When we worked with simplifying of radicals in the past, it was nothing ever so scary as far as trying to find our perfect squares. 4, 9, 16, 25, and so on. When we did that, we were trying to figure out how to simplify things out. And I know we just talked about the square root of 12. We knew that the largest perfect square that went into the square root of 12 was the square root of 4 times the square root of 3. And when we simplified it, you guys all got 2 root 3. Right? When you go to simplify a cube root, instead of looking for perfect squares, you're looking for the perfect cube. So that means we have to start to remember some of these. 1 cubed is 1. 2 cubed is 8. So you have 1, 8. What's 3 cubed?
27.
4 cubed?
60.
Good. And so on and so forth. Okay? So what we're trying to do here is we're looking for the largest perfect cube root that goes into 54. 27.
Yep. I was thinking 56.
So I can break that into the cube root of 27 times the cube root of 2. 3 cube root 2. Because you're dealing with cube roots here. All right? Again, I'm looking for the largest perfect cube that goes into that.
Wouldn't you just do
96 gives you square root. We're doing cube root. I mean 3 of them.
Oh.
Okay. Again, remember how you guys were able to simplify square roots with your calculator by dividing by x squared? What do you think you'd have to divide by now?
X cubed.
X cubed. Your calculator does it for you. Remember the smallest value for the integer in the y column, so that the number of the x column is the root. But the weirdness comes when you have to rationalize, and this is where most people get mad. if I split this apart like the rule tells me, do you agree that we get the 5th root of 3 over the 5th root of 4? I wish, right? Now, just like in the past, we were not happy about having radicals in the denominator. We're still not happy about having these in the denominator. So before we came up with perfect squares. Now I've got to come up with perfect, in this case, fifths. So here's where things get a little bit weird. I know you guys don't know all your perfect fifths. I don't know all the perfect fifths. But I do know I can do this. What's 1 to the 5th? That's 2 to the 5th.
So that's 4 fifths. 20.
32. Is there any number that I can multiply 4 by to turn it into a 32? 8. So what I'm doing here is I'm creating a perfect fifth in the denominator. Okay?
Oh.
5th root of 8 means I can do the 5th root of 8 up here. Again, this is a little bit muddy. There's 2 ways you can look at doing this. You want to create something in the denominator that when you take the 5th root of junk to the 5th, it becomes junk. Okay? You want a perfect 5th root in the denominator. Another way to look at this, sometimes students see this easier via exponents. What's 2 squared? If I wanted to turn that 2 squared into a 2 to the 5th, what would you have to multiply it by? Think about your properties of exponents. When you multiply the same base, you have to add exponents, right? 2 to the 3rd. Sometimes people see it better when you deal with exponents. Because what you're trying to do here is create a perfect fifth. We did. I'm just showing a different method. What I did here is, what is the 5th root of junk to the 5th? Junk. Instead of going through my calculator to figure out all the next the perfect fifths, to see if I can get 4 to go into it, I could always break 4 down into a basis of 2 and try that. Sometimes you can break them down to bases of 3 and work with your exponents. It's just multiple ways of looking at it.
So does that mean you have to multiply the bottom by
Well, what's 2 to the 3rd? 8. I'm doing these exponent rules without writing the exponents. So 5th root of 32 is how much?
1,
2. It's 2. Has the radical gone away in the denominator? All right. What's 3 times 8?
24.
And you're done. Those will take the longest time to get used to. Those will take the longest to get used to. No, it's the 5th root of 32. It's 2. I've simplified it. It's like when you did before. If you had the square root of junk times the square root of junk, you got junk. The radical was gone.
Do you have any tips for like writing it so you don't confuse the 5th root of 24 with 5 times the square root of 24? Because I know that's going to happen to me.
Your best bet is to try to write smaller font.
Okay.
Or maybe when you put your 5th root up here, circle it, that way you know it's a root, not a
Okay.
multiply. Just use a little something like that. Because I know your handwriting is.
Yeah. It's my handwriting. Interesting.
Same thing happens when you're trying to combine like terms. Same thing happens as it did before. In order to combine like terms, you had to have same variable, same exponent. Well, same idea here. In order to be able to combine Like terms, you have to have the same base with the same rational exponent. So in that first example, I have same base, the same rational exponent. I have 6 to the 1/5 of both of them. Not really. I mean, no. But it's not, both numbers aren't being raised to the exponent. So in this case here, again, are these two guys the same? What's 7 plus 2? I can't simplify it any further. That's it. I'm combining like terms. I'm combining things that have the same base with the same rational exponent. When I go to the one over here, I don't have the same nth root. Excuse me, I have the same nth root, but I just don't have the same stuff underneath the radical. Which means I got to create it. Well, is there a perfect cube hiding in 16? What is it? 8. There's a perfect, 8 is a perfect cube. So I can say cube root of 8 times the cube root of 2. I'm simplifying a radical. What's the cube root? What's 16? 8 times 2. 8's a perfect cube. Just like square root of 12 is 4 times 3, 2 root 3. 2 is the cube root of 8, yes. Cube root of 8 is 2. And then I have cube root of 2 left over. Just like you'd have the square root of 12 being 2 root 3, you're looking to see, all right, you are looking to see what is the perfect cube that goes into a 16. Your perfect cubes are 8, 27, and so on. You're breaking apart the square roots, just like we always have. What's the number in front of the radical here that you don't see? 1. What's 2 minus 1? Yeah, a lot of you guys didn't come for a lot of help in chapter 6.1 either, so this doesn't surprise me. It's rules of exponents, guys. None of this has changed from last chapter. I don't mean to put it down here, but this stuff has not changed for any of this. Okay? This has not changed. I'm simplifying radicals. I'm trying to combine like terms. I got to get the same nth root. I drop it down by taking the cube, break down a cube root to get it the same roots and go from there. 2 minus 1 is 1. I've treated it like a variable. I treat it the same way. As long as I had the same nth root, I can combine my like terms. That's all it breaks out to be. That's how every single one of these problems works out. Don't give up. Again, when you're working with expressions here, don't worry about plus minus. What happens a lot of times in these expressions when we're working with variables, we were taking these nth root ones, you should have plus minuses, just like you guys were saying. Why are we having this? The directions in this section will always state, assume all variables will be positive. So when you're simplifying these next styles out, don't worry about doing plus minus. And you're going to be pleasantly surprised that this next stuff is really, really simple. I got the cube root of 125 y to the 6th. When we're dealing with nth root stuff, remember, I'm basically taking the cube root of every single term underneath the radical here. What's the cube root of 125? 5. Okay. Now here's where things get interesting. When you have an nth root problem and you're dealing with exponents with variables on the inside, you ask yourself the next question. How many times does 3 go into 6? Is there any left over? And that's it. And you're done. When you're simplifying via nth roots, it is much quicker. Let me show you the same number with a different exponent, just so you guys get the clarification on that. Again, if it's the cube root of 125 y to the 8th this time. Cube root of 125 is how much? 5. 3 goes into 8. How many times? Twice. How many are left over? So 2 have to stay inside. It's kind of like doing division and remainder. When you're working with nth root, when you're working with your exponents. It is a lot cleaner than the combining of like terms. Working with nth root, you're asking yourself the same question each time. How many times is my nth root go into all of my exponents? And that's how things dump out. How many times does it come out? How many are left over? Leftovers stay in. Same idea. 4th root of x to the 4th, y to the 8th. Very good. When I have to take the 4th root of both the numerator and the denominator, how many times does 4 go into 4? Any left over? Nope. Times 4 go into 8? Any left over? That's how that works. What changes when you have it written in exponential form? What changes when you have it written in exponential form? You use the properties of it. What does 1/2 power mean? Okay. What's the square root of 9? Do you guys agree that I have to take the half power of each one of these terms?
Yeah.
Okay. So I know that's going to be 9 to the half power. When it's u squared to the half power, you have to multiply your exponents, right? What's 2 times 1/2?
1.
What's b to the 10th? So 10 times 1/2. So your final answer is 3 u b to the 5th. You're using the properties of exponents. When you have power to power, you multiply them out. Your fractions tend to disappear. Okay? And this is the style that most of you guys have trouble with. Numerator, we have 6xy to the half. In the denominator, we have 2x to the 1/3 z to the -5. Every time that we do one of these problems, I always try to do the exact same setup. I always work with my integer values first. After that, I make all of my variables positive exponents, and then I simplify. I try not to do too much at once, because that's usually where I make mistakes. So, what's 6 over 2? 3. In the numerator, I have x y to the 1/3, or y to the 1/2. Both of those guys are happy. They don't have negative exponents, so I'm just going to rewrite them. In my denominator, I have x to the 1/3. He's happy because he's positive. Z is not happy, so where do I put him? Up.
And the z goes.
Correct. Now there's only one variable that I have to simplify. The x's. Who wins in the battle of war? A 1 or the 1/3? 1. And we've said this one before. What's 1 minus 1/3? So my final answer is 3 x to the 2/3 y to the 1/2 z to the 5th. Remember, take care of your numbers first. Rewrite all of your exponents to become positive. Then simplify out. And then lastly, last one here. use the nice little shortcut of that fifth power. We got the fifth root of 5, a to the 5th, b to the 9th, c to the 13th. And if I use my nice little shortcut of writing that out, is 5 a perfect fifth? No, so it has to stay inside the radical. And now go variable by variable. How many times does 5 go into 5? Now, I'm talking about the a to the 5th part, not the number 5 out in front of it. It goes in there once, so 1 can come out. Does any stay in? No. 5 goes into 9 how many times? 1 comes out. How many have to stay in? Don't forget my 5 in here. And then how many times does 5 go into 13? And how many are left over? So what happens here is that you wind up with ABC squared times the 5th root of 5b to the 4th c cubed. Is how that simplifies out. And notice, all I had to do was just ask the simple question of how many times does 5 go into each of those exponents? Okay, let's get cut this close. In order to be able to take the cube root, when you have something that is not a perfect cube within the, or I'm sorry, not perfect cube, but when you're dealing with your exponent, if I'm talking about this division rule, 3 doesn't go into 7, does it? What's the next number that 3 goes into, an even, I don't want to say even, but without leftover? Going up. 9. You guys agree? What would I have to multiply y to the 7th by to turn it into y to the 9th? Y squared. So you wind up with cube root of xy squared over the cube root of y to the 9th. You're rationalizing as you're going. It's much, much, much easier to do that with variables than it is with numbers. Because you're asking what's the next number that 3 goes into that's bigger than 7? So 3 goes into 9 how many times? So your final answer would be the cube root of xy squared over y cubed. Yeah?
Wouldn't it be like you take the 7 and you goes into 7 or 7?
Because you're just like a radical in the denominator. You could rationalize.
I need to multiply everything by that.
You get the same result, but it just gets messier that way. If you try to rationalize it first, it's just cleaner. What you're doing is it would work, but then you have a lot of nastiness to work with. Okay? Give these I know there's other stuff to look at, so you'll have to try those, but give these a shot. We'll go through some of them tomorrow. But we gotta hunker down in this class a little bit more instead of being a little bit louder during class because everybody else finished with a lot of time. So, just a heads up.